Today on Inevitable, our guest is Matt Lozak, CEO and co-founder at Aalo Atomics. Matt and his team are building what they call XMRs, or extra modular reactors. They're designing 50 megawatt nuclear power plants made of pods of 5 megawatt reactors each, targeting the data center market. The reactors themselves are inspired by the Marvel reactor design from Idaho National Labs, for which Aalo co-founder and CTO Yasir Arafat was chief designer and project lead. Aalo uses a liquid metal sodium design to extract heat from the reactor core, which they believe increases efficiency and energy output compared to a traditional light water reactor. They're pursuing regulatory pathways with the Nuclear Regulatory Commission for commercial data centers and with the Department of Energy for on-site federal facility usage. Aalo announced a Series A in mid-2024 that included 50 Years, Valor Equity Partners, Harpoon, Crosscut Ventures, and others. From MCJ, I'm Cody Sims, and this is Inevitable. Climate change is inevitable. It's already here. But so are the solutions shaping our future. Join us every week to learn from experts and entrepreneurs about the transition of energy and industry. Matt, welcome to the show.
Thanks so much for having me, Cody. Excited to be here.
I'm looking forward to really getting an update from you on what you're building at Aalo. And let's start there, because I know everyone I talk to pronounces it differently, and you just clarified for me it's Aalo, like all the things.
That's right. Yeah, it's a word that means the light. So it kind of has a multi-layered meaning for us. I mean, on the one hand, we're trying to push towards this bright, optimistic future for humanity. And then it kind of has a few deeper meanings for us as well. So for example, we try to hire optimists, people who believe that what we're doing is possible and want to work really hard at achieving it. There's a few other secret hidden meanings as well that might come to light one day.
Wow, multi-layered. What language is this from?
It's Bengali.
Bengali. Wow, cool. I think that is the only Bengali word I know, that I now know.
Well, it's a good one to know, yeah.
All right, on the notion of optimists, I want to go back to when you and I first met, which is the summer of 2022, I believe. And we got introduced by Ange at Version 1 Ventures. She had met you, I think, as a fellow sort of Canadian entrepreneur. And you had just written this post on Medium, which is titled, Why I Left the 150 Employee SaaS Company I Co-Founded to Get into Nuclear Power. And I think you were obviously wrote that drawing on the fact that you were an entrepreneur, but you also, at that point, I think had very little background in nuclear itself. But what's amazing is Ange connected us, but then I feel like at MCJ, we had 3 or 4 other triangulation points of like, hey, have you met this Matt guy? He's like doing a nuclear thing. And so like you very quickly went out and built a network and sort of just willed your way into becoming a founder in the nuclear space. I want to understand more about that because you now you're in development on a full-scale nuclear reactor. Why don't you describe the journey that you went on, maybe starting with your entrepreneurial path and how you became a founder, and then what ultimately convinced you that you could go do this thing?
It's kind of funny because for a lot of people, they see this guy who had this kind of HR payroll benefits software suite turning into a nuclear founder and thinking, what the heck is that? Looking at the whole kind of life story, it's interesting how nuclear has kind of woven in and out of my life story all throughout. And like the earliest kind of realization for me of how cool nuclear energy is was actually when I was early teenager. And kind of before that, I had pretty bad asthma, breathing attacks. And that was because at the time, Ontario, we had a lot of coal power plants. We actually used to have around 62 smog days per year. But then, very fortunately, the government decided to turn off those coal plants and go all in on nuclear. And it ended up being around 60 or 70% of our grid, with the rest being kind of hydro and basically entirely clean. And we went down to 0 smog days per year, and my asthma went away.
Oh, wow.
So I thought, my God, this is very cool technology. And that was kind of part of what fueled my passion for engineering and physics and science. I ended up studying physics and engineering in university at Queen's, took courses on nuclear, but also other things like relativity and quantum, and even had a lasers course, which I thought was pretty badass.
Awesome.
After graduating, I thought, it's probably pretty hard to start a business right after graduation in the nuclear field per se. So my first business I did was a painting business. I decided to torture myself in my hardest year of my physics degree and simultaneously run this kind of house painting business. So I would, study until midnight, and for study breaks, I'd be doing cold calling to drum up business. Hired 30 employees for that business, and we did $100,000 of painting homes. And I learned that, hey, business is really cool. It's cool to work your butt off and have some success there, but painting isn't the most interesting to me. But I was like, yeah, maybe one day I can combine all these interests. And that was always what kind of drove me, is finding a way to dabble in things and see what I really loved, because I tended to do better at things I really loved. And so I liked business, I liked science and engineering and physics. But then, yeah, because starting a nuclear company after graduating is hard, I thought, hey, let's start in software. I did one company that you might call a learning experience. The second one I started in 2016 with a co-founder, Kevin. So that was the HUMI. So that was HR, payroll, and benefits software. And we became a pretty big HRS player in Canada. So we processed over $7 billion of payroll. We actually just had an exit for over 100 million. So it was a great learning experience and a lot of fun, and learned a lot about structuring companies and scaling and recruiting and all those good things. I wasn't the most passionate about HR software. And so I think that blog post that you're referencing was what I had written when I was, deciding really what is the culmination of all my deepest passions in life. That really was Aalo. And so that's the long story. And if you want, I can dive into how I met Yasir, but maybe if you want to, dig into anything else first, happy to do that too.
That's a great overview, and congrats on the recent exit of HUMI. That happened a few years after you've since departed, but a testament to the company that you helped build. It ultimately, hopefully, turned into a good outcome for you and for the folks you brought on board as well. How did you meet Yasir? He is this very accomplished nuclear engineer. Maybe give us a bit about his background and how you two came together.
So Yasir was the chief architect and project lead on the MARVEL program at Idaho National Lab. This was kind of like a scaled down test reactor, one of the first advanced reactors that was under construction in the US in decades. And it was the first reactor that was ever approved by the DOE for construction. Usually the NRC is the regulator, but for government labs and other forms of non-civilian soil, the DOE can be the regulator. Yeah, Yasir, before starting MARVEL, he also was the person who formed the Vinci program at Westinghouse, which was their microreactor entrant and still is. And before that, he did a lot of R&D and kind of work a little bit on the AP1000. So Westinghouse was kind of where he was the longest after his university degree. So for both he and I, we were both kind of interested in nuclear for a long time. Obviously, he went right into the industry after university. We were both always kind of entrepreneurial minded. I think he also always wanted to start a business. But when we met, it really felt serendipitous because we had a very complementary skill set. We had very similar values and kind of a view of what nuclear should become. And, even kind of a similar sense of humor. And we just really got along quite well, which I think is important, for a co-founder who you're doing this business with for the long run. We met and decided that maybe at some point it would make sense to start a company together, and found a way to make it work.
Help me understand sort of the pathway for building a research reactor at INL like MARVEL, and how it then becomes a commercial project. Does the government still play any kind of role in the ongoing commercialization of the technology? Help us understand how that all works.
So MARVEL was never really intended to be commercialized directly. What it was really meant to do was help catalyze the industry through providing data that can be really helpful for a lot of different players in the industry. So when Yasir was going to pitch this idea to the folks at INL and DOE, the whole intention was saying, hey guys, in the US, we haven't built one of these advanced reactors in a long, long time. First of all, maybe it makes sense just to show that we can do it. There's a lot of value in that. It might sound simple, but just the very act of doing that helps to rekindle and revitalize, like rehydrate these dried up or dead aspects of the supply chain and the muscle of the industry to some extent. That was a big part of it. There was another program called Pele, which is also ongoing, and that's a high temperature gas reactor. MARVEL is a liquid metal cooled reactor. These are both programs that are really trying to help the US just get back into building things. This program is all the data, a lot of the design aspects are readily available to those who want to leverage certain parts of it. So I know some companies have used some parts of the control drum architecture for Marvel. Others have used different parts of the fuel data. These are all meant to kind of catalyze the industry. And so what's been helpful for us is the idea that with Marvel going through that whole process, it's caused the INL and DOE to really think through how to do a lot of these things that are in the minutia of building a reactor that might not have existed had that not been happening. So certain siting processes, certain environmental processes, regulatory processes, supply chain processes, like these are all things that once Marvel and Pele were going through these procedures, now all of us other reactor developers have the benefit of kind of going through a more streamlined process because this was done recently. It's really beneficial for the country for all these different vendors.
And for folks who want to understand more the INL side of how Idaho National Lab is thinking about these programs, we did have Dr. John Wagner on as a guest. I think that was your intro, Matt, originally, maybe 18 months ago or so, as a guest on the pod. And it was a great episode, really full of a lot of insights about how the national labs work, and in particular, how Idaho National Labs is working and a lot of their focus on advanced nuclear reactors. And it sounds like you all have a continued, very deep relationship with INL. I think you're using some of their testing facilities still in a significant way. Is that right?
For our first plant, we are doing DOE authorization as well. This is the Aalo X. It's our experimental reactor. Like I was saying, like leveraging a lot of these pathways that have just been established and now can be used in a more streamlined way. And so the lab has been great to work with. There's a number of other vendors building test reactors at the Dome, which is a famous site. It's where EBR2 used to be. There's a few vendors that are doing NRC authorized plants in the periphery of the land of Idaho National Lab. So there's a lot of different people trying different things. It's pretty exciting.
And will the first wave of NRC work that you need to do be part of that Aalo X project that's inside INL, or is that purely a DOE authorized reactor that you're building?
For us as a company, our strategy on regulatory, we're pursuing the two in parallel because DOE is for non-civilian soil, NRC is for civilian soil. Our estimation is that DOE might be a little bit more streamlined. And so we think that plant might go critical before the NRC regulated plant. But the nice thing is all the engineering work and the math and the physics applies equally to both regulators. It's just packaged up a little bit differently. And one really interesting thing that's actually brewing that I think is worth highlighting, this is kind of hot off the press from the past few weeks even, is we always perceived the DOE authorized plant to be kind of like our calling card, a good way to get the first one built, prove things out, and then scale rapidly thereafter. But we never saw it as a major deployment strategy for scale. However, in the past few weeks, there's been a bit of a sign that Trump and Energy Secretary Wright have been pushing for the deployment of a lot of co-located nuclear and data centers on non-civilian soil. And this is pretty interesting. I think it's coming from a place of really trying to compete with Russia and China on AI and nuclear to make sure we don't fall behind, frankly. What's really interesting is if this becomes kind of almost like a wartime effort of keeping up in this really critical technology, then the DOE authorization pathway could become way more relevant for scale than we initially estimated. Really interesting space right now.
Super fascinating development. Why don't we take a step back, describe the Aalo reactor?
For us, we really focus not just on the reactor, but really the whole plant. The way that we always think of this is that the reactor is not the product. The plant is the product. And the reason this is relevant is I think it makes sense to kind of take a step back and outline how we see the lay of the land in nuclear. So bear with me as I just rant on this for a second. So we think that the ideal way to deploy nuclear in the West and really the world is to mass manufacture it, make these plants in factories. And if you look at nuclear today, it's a lot of bespoke kind of onesie, twosie plants. There's never really been a factory that's mass produced reactors and deployed them widely. And you can kind of, ask why this is. We think that it's largely because in the past, there was this kind of more government-driven utility model where there wasn't really the right type of demand. And taking a step back further, you kind of might want to ask well, what is the right type of demand? What will drive the generation of these factories? And the AI data center movement is so incredibly unique and well suited to kind of be the guiding force that bootstraps these factories for two main reasons. One is it's the fastest growing. And two is it's the highest willingness to pay. We're talking about bringing on tens of gigawatts, which is kind of like tens of new cities. Each gigawatt is like a million homes in a very short period of time, maybe in the next 10, 15 years. Because these data centers are so lucrative, they have a really high willingness to pay for power. And this is, a really, really awesome recipe for getting this factory set up because everyone knows that the first of a kind is going to be more expensive than the nth of a kind. You're going to need a customer willing to pay a bit of a premium for those earlier versions. But then once you get that set up and you've got the repeatability of the factory and the predictability on cost and timeline, it's really this incredible situation you can be in because then you can come down that cost curve and then compete on all sorts of other different markets beyond that initial wedge of AI data centers. So good old fashioned utility, power, and then anything from even new markets like industrial process heat, desalination, chemical processing, all sorts of things. That never would have been possible without the right type of demand to get the factory set up to begin with. And I think it's also worth highlighting why the factory is so important. Again, if you look at all these bespoke reactors that were built before, the hard thing is like a lot of people kind of look at nuclear and ask why we're not building more of it. On the surface, they assume, well, maybe the regulator is stopping us. The thing is, there's actually 8 utilities that already have approved licenses to build large water-based reactors, and they're choosing not to because of a fear of cost and schedule overruns. Again, the reason why the nuclear plant factory vision is so compelling is because it can solve that main problem around the challenge of predictability on cost and timeline. We're really in a really special moment in history now where nuclear, really for the first time in its history, even in the early days, has this chance to set up this infrastructure, which could allow it to be just way easier to deploy. And I think this would be a very good thing for the world because it's clean, it's baseload, it uses very few resources, very little land, it works anywhere. To me, and I'm biased, it really is the ultimate energy source for humanity. I'm really excited because I think the window is open to do something really special here. And we're working our butts off to achieve this vision.
What about your design approach makes it mass manufacturable in a way that a light water reactor is not?
Light water reactors have been attempted to be manufactured in factories before. So the large water-based reactor that was built recently was fairly modular. One of the challenges there was that it wasn't fully vertically integrated. So there was a lot of miscommunication, and that's just a challenge. If you build large things, you very quickly realize no matter how good separate vendors can be, there's just inherent challenges to integrating lots of different vendors.
That's my perception is like a lot of the challenges with the Vogel plant, for example, were challenges of project management, maybe more so than challenges of engineering per se.
Yeah, exactly. So it's worth highlighting this is not purely a technology challenge. But then also you can ask yourself, well, what technologies would be really well suited for mass manufacturing? And for us, one key thing is we think a lot about supply chain and availability and readiness to scale. And one big change we had in the past year was we shifted to a more readily available fuel because just in the name of speed and economics. I'd much rather have an imperfect reactor built sooner than a perfect reactor built later because the world needs this, ASAP. For example, we're using off-the-shelf uranium dioxide fuel that's in a very typical form factor that can be at a very typical enrichment level that can be, mass produced and not only be available for the first reactor, but also be available to scale really rapidly thereafter. So that's one thing. And then another one is if you compare using a liquid metal as a coolant to water, there are a few advantages that we think we can get to. So one is it allows you to make the reactor much more compact and the plant much more compact, which saves cost. Another one is its atmospheric pressure. So the safety case is just a little bit different. It's kind of nuclear is already very safe. The whole idea here is you're going to achieve that same level of safety a bit more simply with these types of technologies. And so the reason it's not an obvious slam dunk, because it sounds too good to be true, is there actually were, a number of groups that did sodium-cooled reactors in the past. And oftentimes they thought it would be this holy grail of economics because of the compactness and the inherent safety and so on. There were some that did have good success. EBR-2 operated for decades with very few issues. So there are good success stories. But there's also a graveyard of a few different groups who just had struggles with maintenance and operations and so on.
Any kind of like molten salts or liquid cooled metals are notoriously challenging to work with, right? So you've kind of got to iron out a lot of the corrosiveness and the sort of all of those bumps when you're actually trying to build these things at scale.
Yeah, exactly. And the way that we think about this is not fusion where there's kind of multiple Nobel Prize winning discoveries that have to be made before it's really feasible or economical. These are engineering challenges. Maybe a good analogy is like SpaceX landing a rocket. Nothing from first principles physics precludes that. It's a tough engineering challenge.
Mhm.
And similarly, our equivalent to landing a rocket might be how fast can we plumb a leak? Maybe we're just glorified plumbers or something.
At the end of the day, it's all a fancy way to create steam, right?
Yeah, exactly. A lot of pipes. So this is kind of our core engineering challenge is to unlock that holy grail of economics. Can we resolve any leaks or clogs in a matter of seconds or minutes instead of months or years? If we can do that, then we'll be in a really good spot. And we're doing a lot of that non-nuclear testing and proving that to ourselves, de-risking in the next 12 months now that we've built the full-scale prototype in the past couple months.
Hey everyone, I'm Yin, a partner at MCJ, here to take a quick minute to tell you about the MCJ Collective membership. Globally, startups are rewriting industries to be cleaner, more profitable, and more secure. And at MCJ, we recognize that a rapidly changing business landscape requires a workforce that can adapt. MCJ Collective is a vetted member network for tech and industry leaders who are building, working for, or advising on solutions that can address the transition of energy and industry. MCJ Collective connects members with one another, with MCJ's portfolio, and our broader network. We do this through a powerful member hub, timely introductions, curated events, and a unique talent matchmaking system and opportunities to learn from peers and podcast guests. We started in 2019 and have grown to thousands of members globally. If you want to learn more, head over to mcj.vc and click the membership tab at the top. Thanks, and enjoy the rest of the show.
One understanding that I have, correct me if I'm wrong, is one of the reasons that in the US at least, reactors have largely been these large facilities is also one of security. Nuclear reactors have armed guards and incredibly tight security parameters around them because, again, you're dealing with nuclear fuels. Is there something about your reactors and others of your ilk that can allow those requirements to be less severe?
That's a great question. And that's one that also people don't often talk to, but can really impact economics as well. For us as a company, we actually did a couple site visits. So we did a site visit to a gigawatt scale nuclear plant. And we noticed that there were 200 armed guards, 7 sniper rifle towers,
Wow.
all these kind of armed kind of security folks. And then we also did a site visit to a 1 gigawatt natural gas plant. And that had the same size power output, but instead of 200, it had like 20 staff and maybe like 6 on site. And it had a badge card entry. There's this question of, can we get nuclear to a point where it looks more like the latter than the former? That has some big economic implications. People often think of the cost of electricity as being a function of the equipment cost. But if you have something generating power over several decades, the O&M quickly becomes a big part of that LCOE, that cost of power. There's actually some good proof points or existence proofs in research reactors. Some research reactors use certain...
And by the way, sorry to interrupt you, but if you take that model, if you have 1 gigawatt plant that requires 200 staff, and you say, hey, we're going to build a bunch of 50 megawatt reactors, and if each one of those requires 200 staff, like you're dead in the water. Your model will not work, right?
That is fair to say. Yeah, we're certainly not planning that. And conversely, I think, and we can come back to this, but the idea of having a shared set of staff and security and refueling infrastructure across a number of smaller reactors is actually a compelling product for data centers because the redundancy of reactors gives them availability. And that is valuable to them. And they're willing to pay a premium for that, especially if it can be delivered quickly. Let's come back to that because I want to finish answering your other question too. So the existence proof I was mentioning is research reactors. There are some that are actually 10 megawatts. They don't have like 200 armed guards. They actually have like a key card system badging in. There are proofs of certain reactors when they have different levels of inherent safety and so on that have been able to negotiate with the NRC around having a simpler safety case because it's warranted. So reactor technology has been developing for 70 years, and it's not all created equal. And it's all safe today, statistically as safe as solar or wind, but that can be achieved in different ways. Mm-hmm. So that's the whole idea here is in this advanced reactor space, can you make it look more like a natural gas plant operationally? And If you can, then boy, oh boy, are the economics going to look good because it's got virtually no fuel cost.
How much of that comes down to how enriched the uranium fuel source is that you're using?
And you're asking in terms of safety?
Yeah.
Enrichment generally...
Security too, just like security requirements as well.
So generally the thing with enrichment is that's largely impacting your refueling frequency. So that's the primary operational thing is if you have higher enrichment, you can let the fuel operate for longer. And then there's this whole financial analysis you can do there on, well, does the fuel cost more upfront? It's a CapEx versus OpEx trade-off with more refueling cost. There are some implications with higher enrichment. So if you take this reductum ad absurdum, where you think about the extreme case, if you had like 95% enriched fuel, that would require very intense security because that's like weapons grade. But that's the whole point of HALEU is below 20%. You can't really make a weapon out of that per se. So
correct me if I'm wrong, but most like large scale light water reactors are not heavily enriched. Is it UO2? It's like 5% enriched roughly.
Yeah.
Whereas HALEU approaches 10 to 20% enriched. So as I understood it, the advanced reactors are actually using a more enriched or getting closer to weapons grade enriched level of fuel. And yet it sounds like they may also have fewer or less severe security requirements than an existing utility scale reactor might.
This would be a topic we could dig into for a while. Maybe the simple short answer is anything below 20%, you're safe.
Okay.
The other things to think about, it's not really going to be a concern about this kind of safety concern or security concern. It would be if it was 95%. That's a different story.
Got it.
But yeah, you're right that a lot of startups are using 20%. We're using 5%. But the reason we're using 5 is not because of security or safety. It's because of supply chain. We want to be able to scale really, really fast. And 5% is what's available. So we're starting with 5 and we're going to push that up a little bit higher based on the equipment that's available at these supply chain vendors like GE Vernova, Framatome, and Urenco to just get this done.
And as I also understand it, there is also with the type of fuel that big utilities are using today in the US, there's a fairly consistent domestic supply of fuel. But as you get into some of these more advanced fuels that advanced reactor projects are using, you start to become dependent on, for example, Russian supply chains, which I know is certainly a challenge given what's going on in the world today.
HALEU was a cool idea from 2005 until 2022, but then Russia invaded Ukraine and the supply chain became a real challenge. And yeah, some companies are switching off, some are trying to find a way to make it work. DOE has announced a few vendors that they're going to give kind of a morsel of HALEU to for their first reactors. But I think, yeah, scaling could be a challenge with that fuel decision. We'll see how things evolve on the HALEU side. Hopefully, we want there to be a big supply chain there because we want to look at that option down the line for ourselves as well. Yeah, in the short term, we're using LEU Plus for ourselves.
And you said that was a relatively recent new choice to use that fuel source?
Yeah. In the past year, we've been analyzing this and talking to the supply chain because we're going to be placing the order for our fuel in the next few months.
Yeah.
So this has been in the works for the past year. We put out a video on used hydride that showed the inherent safety of it and all this cool stuff. But that video was actually, we're like, well, we already decided to kind of move off, but we're like, we might as well publish this video because it's just so cool anyway. It's a really cool fuel. It's just one
That's what's used heavily in France, I believe, if I'm not mistaken, right? URZH?
Well, it's made in France at Trigga International, but it's not really specifically used heavily there. It's used in all the research reactors around the world.
Okay.
Really quick sidebar. This fuel is so inherently safe. You can basically try to make it melt down. You can pull the control rods out, which are usually the thing that slow the reaction. It's like disabling the brakes in your car or something, and it actually just shuts itself off from the physics of the fuel. And what's really interesting is Edward Teller, the person who's behind the most devastating weapon humanity ever created, the fusion bomb, not fission, but the fusion bomb. He created that. And he also then went on to create the world's most inherently safe nuclear fuel, used hydride. I feel like one day someone should make a movie about this stuff. Imagine being a physicist. Physicists don't want to kill people, right? That's not what they want to do. But then the government and the military was like, hey, you guys have this technology. Why don't you guys go make a weapon? And they're like, no, but we want to make energy. Like this could actually solve so many of humanity's challenges. So it's just cool to see the individuals behind this. The same person who made that weapon also made the world's most safe fuel. I think it's a really beautiful story.
And what caused you then to move to LEU Plus?
Supply chain.
Got it.
With used hydride, there were a few challenges. So One was supply chain. That was the big one because we really wanted to be able to place the fuel order in the next few months and start building this plant next year and go critical the year after. There were some other, interesting challenges that I think would have been solvable. So, for example, hydrogen dissociation in the user hydride would cause the fuel to be a worse moderator over time, which would cause the reactor to become less effective over time, or the fuel to be less effective over time, which would have been solvable. But really the main thing is the supply chain. Like, we're trying to set up this factory that can pump out a lot of these Aalo Pod products for these data centers in just a few years. And so you need a fuel that can follow suit with that level of demand.
Awesome. And I know that was getting into the weeds for folks, but I think it's fascinating to hear all of the incredibly complex decisions that go into building a new nuclear reactor design. Everything down from how can I source the fuel? What are the properties of the fuel going to be? What are the safety constraints of it? I'd love to pull us back up a layer maybe. And I've heard you describe Aalo as an XMR, which is maybe different than an SMR, which is the phrase many of us have heard, or small modular reactor. Explain how you think about the difference there. And is there more to this than just sort of a fun branding exercise?
It's definitely a little bit of a cheeky term. I mean, the last thing the nuclear industry needs is another acronym. I think there is some meaning behind it. So the way that we think about the market is that the large scale reactors, the PWRs, and those are great, they're safe and so on, produce a lot of clean energy for humanity. But then you've got all these kind of startups doing these smaller reactors, and there's a whole swath of sizes and form factors. So we tried to dissect that and understand where we fit in. You've got microreactors, which are usually 1 to 5 megawatts. The LCOE is sometimes like 20 to 40 cents per kilowatt hour, which is definitely expensive, but that's okay because their target market is remote diesel. This comes from when you go that small, you have some challenges on energy density and the efficiency with neutron loss and things like that.
This would be like Radiant. We had Doug from Radiant on the show fairly recently. Would be an example, I think, of that type of reactor.
Yeah. So they're targeting military and remote diesel, which is awesome. The world needs that product. But then that product might be more challenging to power a gigawatt data center because having 1,000 1 megawatt reactors would just be, not the optimal solution, let's say, for that scale. And then you have SMRs, so small modular reactors. And this term came about a while ago when the whole intention was kind of scaling down larger scale plants for like a more of a utility model.
And sort of hitting that mass manufacturability that you were hinting at.
Yeah.
That's been the goal of this size reactor, I think, right?
It's kind of funny, the term is almost a misnomer because the goal really shouldn't be to make just a modular reactor. The goal should be to make a modular plant. And whether or not that's what the SMR vision was intending, that is what we think needs the distinction with the whole XMR term. And really, it's almost like it needs a whole new name that says it's just a modular plant. But that's what we're trying to highlight with this XMR vision, is that the whole plant is made in the factory, not just the reactor. This includes, the SC modules, and a lot of the secondary system, the primary reactor, and just lots more, like the whole plant, really.
So basically the containment units, the pad that it sits on, all of the concrete that would need to get poured to create an SMR with an Aalo XMR module, you can assemble all of this, or the vast majority of it, offsite.
Yeah, which again, sounds kind of obvious, but the strange thing is sometimes when you dig into some of the existing designs, they're not optimized in this dimension. So some end up being more concrete per megawatt than any other reactor design. That seems suboptimal. So that's what we're doing. And what's more relevant or more important than this acronym is really exploring what the product is that we're designing for these data centers. So we've had the benefit of having the past 2 years to really talk to a lot of these customers and ask them, what do they want? And if that was all you did, you'd end up with probably a pretty bad product, because you also have to do the first principles physics and see what's economical. You can't just wave a magic wand and do like a Enron egg or something. What we're doing is it's a 5 reactor, 1 turbine configuration called an Aalo Pod. And each reactor is 10 megawatts. So the total plant is 50. And this was very intentional. So a lot of data centers, they get built out in these 50 megawatt chunks. So 50, 100, 150, et cetera. The whole advantage of having 5 reactors is that when any one is down for refueling or maintenance, the others can make up the delta. So this is also kind of called maybe like a N+1 configuration, where you pay a bit of a premium for the extra hardware to be acting as a backup. But that's valuable to the customer because then they have a high availability. And I have to tell you that like the first plant is going to have some capacity factor challenges. That's a given. But the whole idea is at some point, you could actually have these pods allow these data centers to not require a grid backup. And this is powerful being on site. What it would do is basically save time and money for these developers. Time because the interconnection queues can take 5 years sometimes these days, and money because people don't often realize like T&D can be half the cost of delivered electricity. In fact, in the past 20 years, the overall average power price in the US has been somewhat flat, even though generators have been getting cheaper because T&D has been getting more expensive.
What does T&D stand for?
Oh, transmission distribution.
Oh, okay, there we go.
Power-wise, yeah. This world we're about to enter where there's going to be gigawatts and gigawatts of new industrial load, whether it's data centers or even EVs or other forms of industrial load, it makes so much sense to have a product that's well-sized for on-site power production. The on-site part is really valuable. And if you can pay a premium for that high availability with the redundancy, I think you've got a really special product there.
So behind the meter power for data centers in a modular way. And as I understand it too, with many reactors, obviously nuclear is a clean baseload power source, but one of the challenges is sometimes they do have to go offline when you're doing refueling, for example. And as you mentioned, the lower the enrichment level, the more frequently you are refueling the reactors. And so these pods can allow for refueling and maintenance to happen in a way that doesn't impact overall power delivery in a major way. Am I understanding that correctly too?
That's right. So, for example, a traditional gigawatt scale water-based reactor might have to go down for a month every 2 years for refueling. And the way that I think about this is it's kind of like your Tesla or your EV has 100 small battery cells, not one big one. It makes sense. That's on-site power and it's redundant. So same thing for this.
You talked a little bit about, pathways for getting through all of the regulatory requirements on the DOE side. To do this with a data center in Texas or wherever, where the company is headquartered, you need to go through a full NRC process. What does that look like for you?
We've already engaged the NRC. We've submitted our regulatory engagement plan, and then we've also submitted a couple of topical reports. We're well underway there. The whole idea is that the DOE progress will help feed into the NRC in our case. They're kind of parallel, but then slightly staggered. You're right to deploy these by the thousands around the country, especially on civilian soil, will require NRC approval. There's been a lot of great progress at the NRC. So the Danube division is fantastic and they're very efficient. Kairos has been doing a lot of good work on taking a research reactor approach with NRC 104C. So there's been a lot of promise in slowly moving through these steps methodically. I should really say, step by step, ferociously. Not slowly, but it's kind of doing the steps required, but doing so with vigor. Like I said earlier, like the window is open now where, sure, the NRC could be more efficient in different ways, yeah, but never before has there been so much support from the public, from investors, from government, from customers. Now is the time to do this. I think it's going to happen.
I have a philosophical question for you. Some would say, hey, more AI and more nuclear, does the world need these things? Is this an inevitability or an eventuality that we as a planet need? We're putting a lot of resource into two things that have unknown implications for not just humanity, but for Earth, for life. I'm curious how you think about that.
Oh my gosh, yeah. I think AI and nuclear are incredible. I have a bunch of thoughts on this. So first of all, if you think about for humanity, what brings us more wealth and well-being, it's the ability to do more with less. And there's nothing that I can think of in all of technology, all of humanity, that allows for that more than AI and nuclear. So nuclear allows us to do so much more with so much less. And to be more specific, it's like 1 barrel of uranium is equivalent to 2 million barrels of oil and gas. So I'd much rather just mine 1 barrel than 2 million. That sounds a lot easier. And then it's also just because of that energy density, you use a lot more space, a lot less raw resources, and it's clean. So we can do all these things and not poison ourselves in the air or have breathing problems or, cause global warming. And then on the AI side, I've been interested in AI for quite a long time. Actually, one thing I've never really mentioned is I did a small AI startup that I sold for, I don't know, maybe less than six figures back in the day. So one of the co-founders there was Nick Frost from Cohere. So one of the large language model companies. His partner, Aidan Gomez, was one of the original co-authors on the Transformers Are All You Need paper back in the day. So in Toronto, it was a really cool scene of AI with Geoffrey Hinton and a lot of people in there at the forefront. I think AI is just so incredible, the potential for humanity to do more with less. I've had deep conversations with friends about how if we lived a couple hundred years ago, it would have been easier to contribute to the tree trunk of physics knowledge for humanity, for example. And now to contribute in science, you have to be so far down some small branch that it feels like it takes so much longer to require the prerequisite knowledge to contribute.
Hard to be Galileo of 2025, I suppose.
Yeah. Although maybe AI is this whole new tree trunk itself. Demis Hassabis always speaks about this too. When it's used to help us discover new science and accelerate progress for humanity on whether it's drug discovery, a lot of health-related things, especially I think is fascinating because it's very hard to model biology from first principles physics. We don't have the compute. But already with like AlphaFold, we're seeing that actually AI is really well suited for going toe-to-toe with the complexity of biology, so to speak. I think a lot of good for humanity will come from that. And then name your field, like physics, like there's going to be incredible developments in technologies for materials, and maybe it'll help make fusion possible and all sorts of things. So I think there's massive opportunity here. And I think nuclear is inevitable. And I think it's just a question of how fast can humanity wrap its mind around it and get comfortable enough to allow it to help us enter the future.
Matt, that was an awesome way to share some of your final thoughts here on the interview. Anything else we should have talked about with respect to Aalo, with respect to the company you're building? Love to make sure to give you a chance to share anything more.
Thanks again for having me on. Longtime listener. It's really an honor to be here. And we're hiring aggressively. A year ago, we were like 5 or 10 people. Now we're 45. In a year, we'll be 80 or 90. We're aiming to start construction on the first real plant in 12 months. That's our internal goal. Don't tell anyone. We're hiring aggressively to achieve that and aiming to go critical the year after. And so, yeah, hiring, fundraising, if people are interested in investing, we are doing a Series B right now. Otherwise, really appreciate the time and having us on.
Well, thanks for taking the time to share with us what you've been up to and for being one of my go-to people I call when I'm looking to learn more about nuclear. I've always enjoyed our conversations, and it's awesome to see what you've been building.
Yeah, you bet. Thanks again.
Inevitable is an MCJ podcast. At MCJ, we back founders driving the transition of energy and industry and solving the inevitable impacts of climate change. If you'd like to learn more about MCJ, visit us at mcj.vc and subscribe to our weekly newsletter at newsletter.mcj.vc. Thanks, and see you next episode.